maybe at the end a performance issue. It's an added mass. Rain can add mass, but it can also shift maybe the location. And at the end, it's also a qualification readiness topic. Yeah, let's have a closer look at some of those points in a few seconds. What I would like to start with is actually that we are used in aviation to simulate a lot of topics up front, like we do FEM to understand the structural loads, strengths, and stiffness of the airframe. We do CFD analysis to optimize the lift or the drag and flow behavior in general. We also simulate thermal behavior, and yeah, you know it. But I think it's not that common to simulate rain behavior or the impact on an airframe or the aircraft system in general. But yeah, actually it's important. So we don't want to skip tests. That's not what we want to say here. We need the tests, of course, but we actually need to assess the rainwater behavior early on with the same engineering mindset as we do it for structural or aerodynamic aspects, because it is quite important to identify if we have issues with that topic early on. And why? That's actually because it's much cheaper to identify challenges or issues related to rain at the beginning. And here, yeah, actually, it's important that we know that issues with rain discovered late means a redesign. It means that we need to build several more prototypes, maybe. It means that we need to repeat tests, but we also need to, let's say, to extend our development timeline if it's discovered late. And here I would like to quote a study of NASA, which actually says that errors found during integration and test can actually require up to 78 times the effort compared to if we would have identified the issue during requirements or design phase. And that's actually, I think, the most important argument to do it early on and to understand the physics behind. And yeah, actually, that's something that is very interesting to understand, and not only see actually the effect, but also understand the root causes. So we see in tests or in reality at the end where we have wet spots, to keep it simple, but we don't see exactly the reason for it. So here simulation can help a lot, actually. It's an enabler to see the path and the mechanism behind, and we have the option to actually make it visible. So what you see here on the slide, actually, it shows the path of rainwater. And in this example, it's showing an ingress between the control surface and the vertical or V-tail, actually. It accumulates inside the fuselage if there would be a hole. That was just for testing purposes for the simulation. Of course, you don't build it like that, but that demonstrates very well how you can trace the path of rainwater. And so you can investigate impingement, you can also investigate runoff, pooling, the ingress paths, and also how long it stays at certain spots or places, so the residence time.
And
Yeah.
maybe if I just add here, just a few comments from my side also here, because I think simulation just also allows to isolate effects. So it's not only in a very early phase to get an idea about critical design problems, but also if you isolate, it's much easier to do that on the simulation side than on the testing side. Just whenever you do a test, how to ensure repeatable conditions, and with the simulation, you just whatever, let's say, is interesting, you just change a parameter, change a design, and have really immediately the response on the, let's say, design, and that's, I think, also really a big value by using simulation.
Yeah, that's a really good point. People forget often about the repeatability of simulations and only focus on the cost savings compared to building hardware and prototypes, especially early on. But yeah, to have repeatable conditions, and especially with weather or rain, it's quite hard to reproduce your experiments all the time. I think that's a really good point.
Yeah, I fully agree. Jumping to the next topic or subtopic, it's about performance actually. Water accumulation is also a performance topic. I mean, we know it from icing topics in aviation. It's quite important to understand the icing effects. It's about degraded aerodynamics. It's about added mass, but it's actually the same with water. Maybe not with the same extent, but it's the same, addressing the same topic. So rainwater can add mass, especially if we talk about slow flight or hover modes, which are actually a big topic in eVTOL, in the eVTOL world. And also mass distribution, depending on the aircraft architecture, it can shift the CG, it can shift the dynamics of the aircraft. So it can influence aerodynamic and flight dynamic behavior, and that might, or most likely is in a negative effect. So it's good to know that upfront, to test it upfront, and to understand the impact on performance, which is especially important for flight phases where we have margins which are already limited, and that's very helpful then to understand what can add up to a critical situation. Yeah, and then
maybe just also to not forget about whenever we develop new solutions. I think it's not only for sunny weather conditions or nice weather conditions. So at the end of the day, in order to have a business that really works, you need to ensure that you can run it not only on good weather but also on bad weather. So therefore, I think being prepared for all weather conditions, I think, is also something that is important. Or how would you see that, Andreas?
Sure.
What's the status here in the industry?
Sure, you're absolutely right. I mean, it's especially important for the business model. We need to have the aircraft operational as long as possible, including also not, let's say, perfect weather conditions. So I would like to avoid the term all-weather aircraft, but of course we want to extend our operational window as much as possible, because we only earn money with an aircraft that flies and not if it's on the ground. So this is true for manned aviation, but also for unmanned aviation. So very clear yes to your statement. It's very important to extend the operational window, the capability to serve also in rainy conditions, and to be ready for operation for a much longer time. Fully agree.
Maybe rainy condition could even be, let's say, starting or landing on a ship on the ocean. Maybe there might be probably not rain, but there is a lot of kind of heavy wind, and probably also water droplets will just be in the air that even could somehow deposit on the aircraft and probably dry out there, and maybe also could have some impact sooner or later. So it's probably not only the rain itself, but any kind of wind created water droplets could be let's say critical for the aircraft.
Yes.
Yeah. At least at the moment, I think it's still a differentiator when your aircraft can actually fly in all conditions and really also has rain covered and has robust operation in under these conditions. So I think it's it's really impressive, and also really impressive simulations that have been conducted here. And I think we will see a bit more shared by Jürgen later on. But just meanwhile, we're also live on LinkedIn. So if anybody of you have questions out there to Andreas or Jürgen, please free to put them in the comments, and we will get them to them. But yeah, please continue, guys.
Yeah, very important aspects, valid points. Yeah, actually, now we already talked now about some issues to look at, but once we understand the water behavior and once we understand the water path, the next question is actually how do we change what we don't like? So what can we do to add the challenge or to change the challenge and make it a benefit? So simulation results can guide our decisions concerning sealing concepts, drainage path, geometry changes, and we can also place components at a different position if possible. And we can also test this in simulation. We can test it, as you can see here on these two examples here, on this comparison here. On the right side, you see the blue fence that has been added for simulation in the simulation to change the behavior of the water path and to see the effect of it and to investigate it without building prototypes, without extensive testing, to just simulate it and to iterate fast and to investigate mitigations and see if they are successful or not. So I think this is a very helpful approach, a very important topic to also reduce development costs, because you can test several options, iterations. And again, as I said already at the beginning, we already do that with finite element analysis or with computational fluid dynamics. So we are used to do it in other disciplines, but we are not so much used to do it in rainy conditions so far. And I think this is it's possible, and you can get fast results doing this kind of analysis upfront with simulation. Anything to add here, Jürgen? Would you like to?
It's just maybe to explain a little bit on the two animations here. You see the propeller is not moving. So in this case, we are just interested in what happens if you are in the, let's say, parking position and just unloading or loading something. So it's also when the cargo space is open, it can also become critical. So therefore, just in this case, propellers are not rotating because the use case here is just to see whether there is some moisture or humidity getting also inside.
Yeah, true. That's actually a very good point. We will talk about a parallel airstream which alters the behavior again in a few seconds as well. Valid point. Actually, another aspect which I think is also very interesting are the surface properties. So until now, we have mainly talked about geometry, water path, and design changes. But here it's about the surface properties actually. So yeah, droplets do not simply slide off the same way from every surface. And here we need to consider adhesion, roughness. We need to consider contact angle, hysteresis, and yeah, that influences actually how the water sticks to the surface, how it forms films, how it pools locally. And that's very interesting, or it was very interesting during our investigation actually, that you see here the two examples where we just altered the surface properties. So the top one is the baseline and the bottom one is with altered properties. And we can see that we can see in the results that we actually reduced the water mass by 40% just by changing the surface properties. And that's very interesting because this might change your painting, your coating of the aircraft, and can influence your decisions on this aspect. So that was quite interesting, as this case might be important, for example, for a hover case where you don't have a parallel airflow that wipes off the water. Yeah, but that's actually also a good switch to the next slide. We also started to analyze with a parallel airflow. So not only having vertical rain, we wanted to investigate further situations where we have a parallel airflow, for example, ground operation with wind, but also maneuvers in hover, and not only an easy hover situation. We also wanted to investigate forward flight, so cruise flight. And here the situation changes, and the CFD provides actually the wind field, and the SPH analysis resolves actually the droplet impact, runoff, pooling, and everything related to it. So in this example here, if you look at the marked and highlighted areas, you see the wind was coming from from the left. So from a pilot's perspective, from the right front, and you see how the behavior of the water path was changed, and that's especially for the mentioned situations, very important, and also demonstrates the, let's say, the power of these kind of simulation tools.
Really impressive use cases, and also I think is really critical for your design in the end, to make it really robust. We're getting pretty close to the end of the allocated time. I think we started a little bit late, so we can maybe go to one or the other minute longer. But yeah, just to let you know roughly where we are in time.
I'll hurry up. The message that I would also like to place here before I hand over to Jürgen is that we still need testing. We still have to focus on DO 160 testing, but these kind of simulations support this kind of testing actually. So we can already identify with simulation the relevant test cases. So where we have to have a closer look at. We can also identify critical areas and the inspection focus. So where to put sensors or cameras during the physical test. And also, can decide on the on the rain intensity that we want to look at, and so on. So still, testing is very important. It remains in place, but we can make it more efficient by using simulation upfront. Yeah, and with that, I would like to hand over to Jürgen, actually.
Yeah,
Yeah, so
you
just,
were directly included in the project on the AVL side. If you could maybe just give us a very quick background on the simulation technology that was used.
Yeah, so just take the last few minutes. I hope you can see still the same slide. So we heard now quite a lot about the simulation motivation and the use case. We of course now want also to share a little bit about what tool was used and what kind of methodology. So we're using here PreonLab, which is an SPH based approach. So it's CFD like, but the big advantage is you don't have to care about meshing. So you directly can load your CAD data in. You just specify easily the positions of nozzles, and you can immediately start simulating. And most of the time, people just are interested in getting the results. So that's quickly really also possible with all the latest and greatest support also from GPU. So very powerful simulation capabilities here. And as you also have seen from Andreas' presentation before, it's not only considering here the geometry, but also the flow conditions. So we couple it together with a 3D CFD flow field. So that's already on board. So it's, of course, it's an SPH code, but it has the capability to consider three-dimensional flow conditions. We did it on purpose just in the parking position, but there is no reason to not also simulate flying conditions with rotating propellers, or just easily tilt or turn the aircraft and look from different positions. And just to give a number here, also calculation time, for example, 6 hours for 30 seconds real time, really very fast feedback on, let's say, design decisions. And of course, there's still work left, or there's a number of other things we already have in plan. So it's also about, as said, physical testing support, the test preparation, and that's also what will be done next. So it's also to get a better understanding how to do the test and then to do the comparison. But most of the time, of course, everyone is interested in validity or validation, but the real engineering task is do first the prototype virtually, do, let's say, design optimization there, and then go on a proving validity. But of course, we also can consider that. And next step, for example, also would be consider rotor effects and those kind of things. So just as a quick outlook, that's also on our roadmap.
Yeah, excellent. Yeah, thanks both of you for the presentation, and yeah, really impressive results. If anybody of the viewers would like to get a trial of the methodologies, of course, we are happy to yeah, hook you up either with a cloud trial or just a license. You might also reach out for more technical details, and we connect you directly to Jürgen and Andreas, and hopefully we see a lot of APELEON aircrafts in the skies very soon, also here in the US. Yeah, with that, I like to also say thank you for this week. Next week, we have another interesting episode, more focused on the powertrain development of eVTOLs, especially the safety aspects of the battery. And with that, I wish you a wonderful rest of the week and hope to see you next week again. Thank you all. Perfect. Yeah. Yeah, we didn't lose too many minutes on LinkedIn, and we have the YouTube link that we also provide as a backup for the intro. It was not your fault because the link was different when Kelly sent the second link. So